Exercise 8.1 on graphing circular functions. The first concept we're looking at is our refresher of basic trigonometric equations. In this example here, we've got example 2. If sine theta equals 0.3 and cosine of phi equals to 0.8, find the value of sine pi on 2 minus phi. This one is all about the reflective properties of our unit circle. I'm going to very briefly draw out an example of what I mean. Alright, let's do me a favor and pretend like that's a perfect circle. Of course, if it's cosine phi equals 0.8, that means it's going to be in quadrants 1 and 4, because cosine's positive in those. Therefore, I'm going to make the point that it's right here, and pretend, or not pretend, but assume that line there, right, of course, not the best triangle, but this one right here is 0.8, and that one there is going to be my phi. If I then reflect it, and I say, well, sine of, now I'm going half pi, or pi on 2 minus phi, I'm reflecting, I'm going pi on 2, and then minus our phi, we're going to get something that looks a bit like that, okay? And that value, because it's sine, right, which is the y value, of course, that being 0.8 means that equals to 0.8 as well. Alright, so we're referring to the reflective properties because the 0.8 is the x value of the original of just phi. Right, if I look at the y value of the pi on 2 minus phi, it ends up being 0.8 as well. I'm going to go through example 3a, and then I'll move on to solving trigonometric equations. Given that sine x equals to negative 5 on 13, and pi is less than x, which is less than 3 pi on 2, of course, implying that it's got to be quadrant 3. Okay, very important that we get all the information we can. Find cosine x and tangent. Of course, I'm going to go ahead and draw my diagram. Given that it's in quadrant 3, and because it's a negative sign, of course, it's going to be quadrant 3 or 4. I'm going to pick a point right here. Again, pretend like there's a unit circle there. I know that the sine, or the y value, is going to be negative 5 on 13. Just to be super clear, I'm listing this as negative 5 on 13. Technically, the distance isn't negative 5 on 13. You know that. Distance can't be negative. And then, of course, that's going to be equal to 1. Right? We're looking for cosine x, which is, of course, going to be the x value, or x ordinate. We have cosine x squared plus negative 5 on 13 squared. You probably don't even need the negative, let's be honest, just 5 on 13 will suffice, equals to 1. Using our basic Pythagoras theorem, you end up with cosine x equals to the plus or minus of 12 on 13. Is it going to be positive or negative? Negative, good, because it's of course, a quadrant 3, therefore it's going to be negative 12 on 13. Yes?
Couldn't you take the inverse sine of negative 5 on 13 to get x and plug it into cosine and tangent?
Absolutely could. But that would be using a calculator, because negative 5 on 13 is not one of the exact values that we know, but you'd require a calculator. Yep. From there, of course, tangent is just going to be sine over cosine. So the sine is, of course, negative 5 over 13. And our cosine is going to be negative 12 over 13, which gives us an answer of positive 5 over 12. I'm going to swiftly move on to the solving trigonometric equations. Any questions about this one before I move on? Okay. Moving on to solving trigonometric equations, I'm just going to go through the first two examples because, well, I want to focus on graphing. So, of course, using the exact values, we can work out the solution. Solve the equation sine theta equals to negative root 3 on 2. Of course, the negative is important. Just a quick note. Please don't write theta. Like, for example, we know that reference angle is going to be pi on 3 because it's root 3 on 2. Use your exact values, triangles, or your table, etc. Please don't write theta equals to pi on 3. All right? The reason that's wrong is because later on, that's not one of your answers. And if you write now theta equals to pi on 3, that is incorrect. What you mean to say is that your reference angle, and you can just write ref equals to pi on 3. Right? They'll know what you mean, right? But don't write theta equals to pi on 3, because if it's not one of your answers, and later on you don't remember to exclude it, the examiners will assume that that's what you meant. That is one of the answers. It's not, right? Of course, because it's between negative pi and pi, right? Of course, that is our quadrants 1 and 2. So it's going to be somewhere here and somewhere here. So not 1 and 2, my apologies. Quadrants here to here. Let's do that. Negative pi to pi. So I'm going to have an answer, given that it's a negative, it's going to have an answer down here and down here as well. There we go. Answer's down there. Therefore, it's going to be theta equals to negative pi. Oops, equals to negative pi plus pi on 3. And negative pi on 3, which simplifies down to negative 2 pi on 3 and negative pi on 3 as well. Hopefully this seems quite familiar. The only other step for us is looking at the transformation. So of course 2 theta. There's a couple of ways you can do it. I'm going to redefine, and the reason I redefine it is because I changed the domain as well. But I'm going to redefine 2 theta. I'm going to let 2 theta equal to, let's just say x, makes it a little bit easier. And let it equal to x. I have sine of x equals to root 3 on 2. That means my reference angle is going to be pi on 3. Okay, and of course, because I've got x equals 2, given the fact that it's in, well, same idea, it's going to go through every quadrant, but from negative pi to pi. But our new domain, given that our new domain where x is an element of negative 2 pi to 2 pi, there we go. Alright, remember, because I'm expanding my domain, I'm multiplying it by 2 because I've multiplied my 2 theta, my theta by 2, sorry. Therefore, I end up with the answers of pi on 3, pi minus pi on 3, negative pi minus pi on 3, and negative 2 pi plus pi on 3. Of course, once you've simplified that down, you can't just leave it as x equals because you've defined that yourself. We need to write it out as theta. So once you've grouped it up, you've simplified it into one fraction, you then divide by 2, and you end up with pi on 6, pi on 3, negative 2 pi on 3, and negative 5 pi on 6. If none of this looks familiar, please go back and revise the trigonometric equations exercise, sorry, I think it's chapter 3. Okay. In your own time, you're welcome to complete question C. That's applying a different type of transformation, but the general principle is the same. All right, let's move on to graphing. Can I get you to flick through to page, what is it on yours? Page 8? No, page 9 on yours, thank you. Page 9. We're going to be spending quite a lot of time on this one, so I do apologize in advance. I am going to be talking quite a bit. Did we do sketching trigonometric graphs last year with transformations? Okay. All right. The general transformation principles are quite similar for any of our functions, keeping in mind the general form of our function. That's more applicable in question B. But of course, there are a couple of bits of key information we must note before we graph, right? That's what I think is important. For one, I'm going to write down the transformations. I think that makes it a lot easier. So one, I know that's a transformation. Remember Dr. T, dilation, reflection, translation. It's a dilation. And because it's not explicitly asking for, it's not explicitly asking for like the transformation steps, I can write it really informally. This is more just for me, right? I know it's dilated by a factor of 2 this way, right? Vertically, and I also know it's dilated by a factor of 1/3 horizontally. Right, that's just our same stuff from earlier in the year. And of course there's a translation as well. Translation of 2 units, oops, wrong way. 2 units down, right, because it's a negative 2. Bam, done, okay? A couple of other things I need to note. I need to note the fact that it's an amplitude of 2. Right? If you want to skip the step, you're welcome to skip it and write straight into the fact that there's a range. There we go, the range, right? Given that because it starts off as a sine function, which goes from -1 to 1, right? We're dilating it by a factor of 2, so it goes from -2 to 2, and then I'm subtracting 2, so it ends up going from, I don't want to write equals, I just want to write the colon, goes from -4 to 0. Right, and I'm just applying my basic transformation information, bars. I know the shape of the graph, right, is just going to be a normal sine function. It seems very obvious, but I feel like it's very important to include that. And of course, our period is going to equal to, and hopefully remember 2 pi on n. Sound familiar? 2 pi on 3. Kind of thrown you in the deep end with this question, and it is a little bit trickier, but I am going to jump right into one of the more complex ones. Okay, you're expected to know how to graph your basic sine graph. Here's where it gets a little bit messy. So I'm going to first go ahead and draw my axes, right? Keeping in mind the fact that it goes from negative pi to 2 pi. So I'm going to say that's negative pi, and I'm going to say that's pi, and that's 2 pi. Given the fact that this function does not have a period that's a multiple of pi, right, we're going to have some very odd looking anchor points is what I call them, or key features. If you were to substitute, I'm going to scroll up so I have a little bit more space. If you were to substitute x equals to, so at x equals to 2 pi, you actually end up with y equals to 2 times sine of 6 pi minus 2, which gives us an answer of negative 2. And do the same thing for x equals to negative pi. And by the way, the reason I'm doing this is to find endpoints. And you also end up with, and I'm not going to go through the same steps, I'm just going to write negative 2. Right, I'm assuming you're okay with that. So we actually end up with negative 2, negative 4. We end up with these points right here. And it's not perfectly in line on mine, but hopefully it is on yours. I'm putting negative 4 now, by the way, because I know my range is from negative 4 to 0. There is no horizontal translation, right? So I know it starts where on the same y-axis, so I know that it goes here, starts here. Now, what we can do is, and this is something that I personally do, that probably isn't best practice, right? I like to, when I'm sketching in pencil, draw out a line that I know it's going to repeatedly hit. Not an asymptote, it's just a line that I can refer to. I'm going to draw a line across, and this is, I'm using this as pencil, pretend it's pencil, that I can rub out later. I know it's going to consistently reach negative 2. I also know it's going to consistently reach negative 4. That's going to be my minimum. And I know it's going to reach 0, but I'm not going to bother drawing that. Okay, so what I'm going to do now is I know it starts at 0, which means that one period later, it's going to end up at 0 again. So end up at negative 2 again, right? So it starts at negative 2. So 2 pi on 3, I'm going to say it's approximately here. 2 pi on 3, right? And I know it's going to end up here again, right? That's one period later. I'm going to do the same thing. I'm going to add another period, which is 2 pi on 3 plus 2 pi on 3, of course, gives us 4 pi on 3. I'm going to say that's approximately here. I know it's super faint on yours, right? But you shouldn't be drawing the dotted lines in your final answer, okay? That's just there to, like a guideline to help us out. I know it will reach there again. Oh, wrong color. There we go. If I add another 2 pi on 3 to that, end up with 2 pi. Perfect. Right, 6 pi on 3. Perfect. I know it's going to go through there. So, because I know the shape of my graph goes up and then back down, right? In one period, it should go up, down, not up. So a lot of students make this mistake, right? That is incorrect. One period goes through all of it, so it should go up to here, back down, up there. Up to here, back down, up there, like that. It should look like this. It is a included point, so therefore 2 pi negative 2 should be a closed dot. You apply the same thing going backwards, which gives us a negative. Of course, that gives us to negative. Here we go. We end up with negative 2 pi on 3. Negative 2 pi on 3. This is not the best graph, but I'm hoping, again, yours is a bit better. And it'll look like that. Nostalgic, gross, disgusted, how do we feel? Okay. On a scale of 1 to 10, how much do we hate this right now?
1.
Okay, good. So you'd like to move on to the next one? Great. Okay. I'm going to move through the next one a little bit quicker because I want to focus on question C because we didn't really do tan as much last year. So same idea. I'm going to find out the same information as before. I'm going to find my transformations. So I know it's dilated. I'm just going to write D just so I know it's dilate, right? Dilate by a factor of 2 this way. And it's also dilated again by a factor of 1/3 this way. don't forget it's 1/3, not 3. Okay, it's opposite for our x values. And then of course there's a translation. Right, a translation of course is going to be in the positive direction of pi on 4. Again, please note the fact that this is very important. Do not expand it to 2 cosine 3x minus 3 pi on 4. Right? In this form, we take the dilation, reflection, then translation. So it's still a positive pi on 4 translation. The range is going to equal to negative 2 to 2. It's just the cosine function, which goes from -1 to 1. It's dilation, -2 to 2. And no vertical translation. The period, same idea as before, is going to equal to 2 pi on 3. And the shape of one period is going to look like this. Hopefully a little bit better than this. Let's try again. There we go. Might be a little bit better. Of course, just the general cosine function. At x equals to 2 pi, right, that's my endpoint. I'm going to let you be able to solve that yourself. It ends up with being negative root 2. And then at negative pi, it's going to equal to root 2. Again, you're expected to be able to solve that one by hand yourself, using exact values. Let's draw our axes. So our axes, again, it's going from negative pi to 2 pi. I'm going to go ahead and draw my graph like this. I'm going to put in, let's say, negative pi. And then let's say that one's going to be pi, and this one's going to be 2 pi. I know that my range is going to be from -2 to 2, so I'm going to go ahead and put those in as dotted lines that I will remove after the fact. So 2 and -2. Should probably actually write that one in pen. 2 and -2. It's translated, which actually makes our life much more difficult. Our first, because it's translated to the right, pi on 4, I know that the first starting point, quote-unquote starting point, is going to be at pi on 4. Oops. So, I'm going to go ahead and do a dotted line down, pi on 4, and I'm going to put a dot right there, right? Every period afterwards, so when we add 2 pi on 3, is going to be after pi on 4, which means the next one's not going to be 2 pi on 3, it's going to be 2 pi on 3 plus pi on 4. Yeah? So this one right here is pi on 4, 2. As you move across, the next one is going to occur at 11 pi on 12, which is approximately, I'd say a little bit closer than that. 11 pi on 12, I probably should have given more space, which is going to be up here. When you add another 2 pi on 3 to that, it's going to be at 19 pi on 12, which is, I'm going to say, is approximately here, 19 pi on 12. And we can stop there because the next one after that is going to be past 2 pi. If we go backwards, it is -5 pi on 12. So pi on 4 minus 2 pi on 3 gives us -pi on 12. -5 pi, sorry. -5 pi on 12. I know it's really faint, I do apologize. Of course, that is going to give us that point there. And of course, because it's got symmetrical properties, I know that's going to end up being at -2 in the middle of these points here. I'm going to go ahead and try my best to fill in the gaps now. Okay, so we start off here, goes back down, comes back up, goes back down, comes back up, goes back down, goes up to negative, because of our point from earlier, 2 pi, comma, -√2. Going backwards, it's still going down, back up. Let's do that one again. Down, back up, and then down, back up. This one goes up to -pi√2. It's been 20 minutes. I do apologize, but we do have one more to go through. I won't go through the next one in its entirety, but I will go through the general approach. Okay, next one. Very quickly, same idea. However, there are a couple of very minor differences. Please note the shape of a tangent function is not the same. The tangent function, of course, is going to be the shape of, right, because this is a positive one, it's going to look like this. Very key point, this right here is not a stationary point of inflection. It is a point of inflection. If you have a calculator, you're welcome to sketch it and find your point of inflection. It is not a stationary point of inflection. The gradient is not 0. Our transformations are going to be a dilation of vertical times 3, or dilation of factor 3, and then a horizontal is going to be 1/2, given the 2, right? And then a translation, of course, is going to be a translation to the right of pi and 4, and a translation down of 2. Okay, I'm not going to draw the entire graph, I'm just going to do a period, okay? So, oh, sorry, I've got the period, yes. Period, of course, is going to equal to, not 2 pi on n, but it's going to be pi on n, which in this case is pi on 2. Okay, so we draw our axes very roughly. Hopefully it's a lot clearer. I'm going to put in as my quote-unquote guideline is -2, because I know it shifts down by 2. So let's say that's -2. And then I'm going to shift it to the right by pi and 4, because that is going to be our horizontal translation. And then because I've got that point right there, I know that's where it starts, I'm going to start drawing my tan line. The next one, right, of course, I'm just going to add my period, which is pi on 2, add pi on 2, add pi on 2, etc. The next one appears at 3 pi on 4, and I do the same thing, right? Of course, labeling all key features for tan graph, you need to label the asymptotes as well. Do you want me to go into more detail, or are we okay to give it a shot now? Okay. Alright. I'm very